wave motion. Now, we think of waves, we think of the motion of something, but it's actually not the motion of a medium. Waves are actually energy that is propagated through a medium of matter. For instance, here are some mechanical waves that require a medium. Ripples in water. We can see water moving, and we can see the ripples moving, but the water is just moving on a local scale. And energy from one portion of the water is being transmitted to the next portion, and then transmitted to the next portion. So the water moves locally, but the energy is what's being propagated through the water. We don't actually see water coming from one location going to another location. It's the energy transported through that medium. Sound. Sound needs a medium. It needs air. And it's the motion of air that allows sound to take place. Sound is actually a pressure wave through the air. So when I'm talking to you, I'm creating a condensation and rarefaction of the air, a pressure wave that travels through the air towards you. And when it hits your ear, it moves your eardrum back and forth, and that frequency of the motion back and forth on your eardrum is interpreted by your brain as sound. So sound needs a medium. Fields of grain. Let's say you went out and looked at a wheat field, and you see all these stalks of grain, and along comes a gust of wind, and it pushes on one side of the field, the grains over to one side, and they push over their neighboring grains, and so they're pushing in successive order. Each location is pushing the next locations of grains of wheat. And you can see, as from this initial disturbance of the wind, that this wave travels all the way along the field. So you don't actually have stalks of grain walking their way across the field. You see that the energy is being transported from one side of the field to the next, but that the medium, the grains themselves, are actually just moving locally and not actually transporting. Waves on a string. You can have a string initiate a wave. You can watch that wave pulse travel all the way down the string, but you don't really have pieces of the string over here moving to this location over here. It is the energy that's being transmitted. Locally, the string is moving up and down, but it's not actually moving in the direction of the wave. Earthquakes. You could have a lot of energy in the epicenter of an earthquake, and that energy will move through surrounding ground, and that ground will contact the ground around it, and that will start making that ground move, and you'll have this local variation of the ground. As this energy is being transported from location to location, eventually it reaches the surface, and it reaches maybe Los Angeles or someplace like that, and if you're there, then that local ground will start moving and you feel the earthquake. But you don't actually have ground of earth, moving from the location of the earthquake to the location where you are, where the earthquake strikes. Just the energy. So these are all concepts of mechanical waves. Mechanical waves need a medium in order to transmit this energy. But there are waves that don't require a medium, and in particular electromagnetic waves, light. This threw scientists off at the late 19th century who were studying light because they knew light was a wave, and they knew that all the waves up to that point had required a medium. So they automatically associated a medium with light, and that search for that medium proved to be fruitless. In other words, they found that there was no medium for the light, and this actually resulted in a Nobel Prize for Michelson-Morley in their famous experiment. Types of waves. We can have a transverse wave, where the medium actually moves in a transverse direction to the actual direction of propagation of the wave. Here you can see the wave is moving to the right, and the actual string is moving up and down. So there's a 90-degree angle between the direction of motion of the wave and the direction of motion of the medium, and that would be a transverse wave. as opposed to a longitudinal wave. Say if we were to set the spring here and start a disturbance at one end, cause a quick rarefaction or a quick condensation of the spring, you can see that condensation move along the spring, but it is the energy moving and the changes happen locally. They're both traveling in the same direction, but the local changes are happening like this, and the wave is continuing on in the right direction. So that's a longitudinal wave. Let's see if I can show an example. Here's a spring. If I initiate a pulse on this end, I can see that pulse travel along this spring, and for that matter, if I do a transverse wave, I can create a pulse moving along this spring as well. I hope that worked. A water wave is a combination of both. If we think of a wave in a sinusoidal sense, if you have a transverse wave sinusoidal and a longitudinal wave sinusoidal, you combine those two motions, you actually are going to end up with a circular motion. And you think of a water wave as being a overtow, undertow type effect. So locally, the water is moving like this, transmitting its energy to the next local part of the water, and that's moving like this, and so forth and so on. So you have energy moving along the water, but you don't actually have water from this location moving to this actual location over here. So you could have a wave, you could have a disturbance, say, off the coast of Peru, like an earthquake or something, and that might cause a wave that travels the Pacific Ocean, doing this overtow, undertow effect, transmitting its energy across the ocean, and then finally you get to the continental shelf of Japan, and the water's doing like this, and it's got no more water to pull, so it pulls all that water out from the shelf, and then slaps the tidal wave down on the coast of Japan. But you don't actually have water traveling from Peru to Japan. You just have this energy traveling, transmitted through the ocean. You could actually have a ship in the middle of the ocean, and this wave could travel right underneath the ship, and the ship never knows that that was a huge wave traveling on its way towards Japan. The equation of a one-dimensional traveling wave moving to the right is given by y equal to f function f of x minus bt. So the y is a function of x being our spatial component, t being our time component. We have a name for this. We call this the transverse displacement, since it really is the transverse displacement of the medium as this wave is moving to the right, or wave function. This is a wave function describing the motion of our wave. If you can put the motion of the wave in this form, a function of x minus vt, then you can identify the velocity in this equation. X with no coefficient in front and minus vt, the velocity of propagation is that number in front of the time. Let's see how this might work. Let's say I have a wave that we've described spatially in x and y, and we can see it in this graph here with as it's moving to the right in the x direction, and it's moving with some velocity v. So we're going to look at this as a snapshot of time at t equals 0, and we'll say that at this point the function has this value, f of x. A moment later, sometime t, this is moved to the right. It's moving at velocity v, so it's moved a distance v times t, and the value of the function at that point is actually equal to the value we had at t equals 0 when it was v times t distance before on the x-axis. So that value is the same, and so at time t, we have the function that is equal to x minus vt. So, in essence, this wave moving to the right at velocity v is the same as if we had a function of y equal to fx minus vt. And we can realize then that our velocity is v, and moving to the right is designated by the minus sign in this function. Conversely, if we were moving to the left, we'd have that y is equal to a function of x plus vt. Let's try this out with an arbitrary wave function. It actually is a difficult wave function. We have y of x of t is equal to 5 e to the negative x plus 5t squared. So I have everything going on here. I have exponential, and the value in the exponential, the exponent is squared. Pretty complicated. But if I were to ask where's the direction of motion of this wave, I could describe this wave in its simplest form as a function. Everything going on is a function, when it comes down to it, of x plus 5t. And if I can do that, put all this into a value of a function, then I can identify here that the coefficient in front of the t is my velocity, and because it's x plus 5t, it is moving to the left. So I'm moving to the left with the speed of 5 meters per second, and that's it. If I can describe my function in that form, x with no coefficient plus something t, then in this case I'm moving to the left, and I have a velocity of whatever's in front of the t. So we have this wave. It's moving in the x direction. And since we just got done with the chapter on simple harmonic motion, we really have something here that's repeating itself both in time and in space. You know, we think of simple harmonic motion. We had this motion here where it was actually going about some equilibrium value, and it was repeating itself in time. So after a time period of t, it would actually find itself at the same position as it was t before. Well, in this case, we have this going on, but we also have a spatial movement going on as well. So we can think of this wave as, in a sense, repeating itself in time and repeating itself spatially in the x direction. The distance that it takes to repeat the wave is what we define as the wavelength. So the wavelength, designated by lambda, is the minimum distance between 2 points on the wave that behave identically. And we can define the frequency as a time rate at which the disturbance repeats itself. So if this wave were moving to the right and you focused in on one point as this wave is going by, you would see that the wave is going up and down. And if you were to measure how many times it went up and down per second as it went by you, that would be the frequency. One over that is the period. So, and vice versa, the frequency is 1 over the period itself. So if I were to focus in on this wave as it's going by and measure the time it took to repeat itself, that would be the period. Turns out that the velocity of propagation of the wave is equal to the wavelength, lambda, times the frequency. And we can see that this has the proper units. If wavelength's measured in meters and frequency is per second, then we have meters per second for the velocity, and that is the proper units for the velocity. In general, we can describe the wave motion as a wave function, y equal to a sine something in front of the x, kx, minus omega t, minus a phase angle phi. We define the k, which is the number in front of the x, the spatial component, as the wave number, just as the number in front of the t is the angular frequency omega, and the number out here is our phase angle, phi. We would realize that this wave function should repeat itself every time that we go a distance lambda. So once we go a wavelength, we'll find the same equivalent type of point. So in order to repeat this, if I were to increase x by lambda, that would be the same as increasing everything inside the parentheses that I have right now by 2 pi radians, because I know that the sine function circles around and repeats itself every 2 pi radians. So I can do this. I can add a lambda to my x, which should repeat itself, and that would be the same as adding 2 pi to what's inside the parentheses. I've gotten rid of the phase angle already in both of these sides of this equal sign. Let's see what happens when I set these equal. I'm going to get rid of a kx on both sides and a minus omega t as well. And so I'm left with k times lambda over here is equal to 2 pi. In other words, my wave number, k, is equal to 2 pi divided by lambda, or 2 pi over the wavelength. So our wave number is going to have units of meters to the negative 1, and it's related to the wavelength itself. So if I could see what the k number was, I could use that number to figure out what the wavelength is, because equivalently I could say that the wavelength is equal to 2 pi over the wave number k. Since the wavelength is equal to 2 pi over the wave number k, and the frequency is the angular frequency divided by 2 pi, we can find another expression for our velocity of propagation. Since the velocity is the wavelength times the frequency, it would be equal to 2 pi over k times the angular frequency omega over 2 pi. 2 pi's cancel out, and I get that the velocity of propagation is equal to the angular frequency omega divided by the angular wave number k. And this would be just as equivalent as saying the wavelength times the frequency. Let's try this out. Here's a wave function. Y is equal to 0.25 meters sine 0.3x minus 40t. We want to find a few things about this wave function. X and y are in meters, t is in seconds. Determine for this wave the amplitude, the angular frequency, the angular wave number, the wavelength, the wave speed, and its direction of motion. Now, if I'm looking at this wave function, something times sine of something, I know the sine function can never be greater than 1, at least in magnitude. Always going to be dominated by 1. So truly, what's out in front of this wave function is my amplitude. And hence, my amplitude is going to be 0.25 meters. It can never be greater than that. So that would be my amplitude. Angular frequency, we just said that whatever's in front of the t is our angular frequency omega. So omega is going to have to be 40 radians per second. Angular wave number, whatever's in front of the x is our angular wave number k. That's going to be 0.3 per meter. Wavelength, we're going to have to do a calculation for that. But we know that the angular wave number is 0.3, and the wavelength should be 2 pi over the angular wave number k. So our wavelength should be 2 pi divided by 0.3, whatever that is. We'll figure it out in a moment. Wave speed. The speed of propagation of this wave should be the angular frequency 40 divided by the angular wave number 0.3. So 40 divided by 0.3, whatever that comes out to be. And the direction of motion, since I have kx minus omega t, the minus means that this wave is traveling to the right. So let's repeat all this. Here's our wave function. Here's the amplitude, angular wave number, angular frequency. I can get the wavelength from the angular wave number. That's 2 pi over k. 2 pi over 0.3 is 20.9 meters. So there's our wavelength for this wave. I can just extract it right from the wave function. I can get the velocity of propagation by the angular frequency omega over the angular wave number k. And that's 40 divided by 0.3, or 133 meters per second. And this wave is traveling to the right. So, very nice. A lot of information in this wave function. Now, something is slightly perplexing here, because just a moment ago I said that if you could put a wave function in the form of x minus vt, that whatever's in front of the t would be your velocity. And here we got 40 in front of the t, and then we just calculate our velocity of propagation to be 133. So what's up here? Well, I have to put the function in the form of x minus vt, where x has no number in front of it, just 1. And so if I were to take this function to try to put it in that form, I would have to factor out the 0.3 from the parentheses. So I would have the sign of 0.3 times, in parentheses, x minus 40 divided by 0.3 times t. Now, if I put this function in that form, then what was in front of the t would indeed be my velocity of propagation. It would simply be 40 divided by 0.3. And hence, so I can see from that aspect that my velocity of propagation should be the angular frequency divided by the wave number. So I would get a number 1 in front of my x in order to put it in that form of x minus vt. So everything's fine. We are consistent. Here's another wave function, y equal to 0.12 meters sine pi, in parentheses, x divided by 8 plus 4t. Great. What do I want to do with this? I want to determine the transverse speed and the acceleration of this string. It's a transverse wave on a string at 0.2 seconds for the point on the string located at x equal 1.6. Now, what do we mean by transverse speed? We've been talking about speed of propagation, but what is the transverse speed? Well, the speed of propagation is when the wave is traveling and propagating in some direction. We've been choosing x for that. But the transverse speed is how fast the medium is moving as it's moving in a transverse direction, 90-degree angle to the direction of the wave. So we know that the wave function describes a position of the medium as a function of position x and time t. So y is our y position as we're going in a transverse position. So the derivative of that position with respect to time should give us our transverse velocity, or transverse speed in this case. Because we have our position, we take our position as a function of time as it's changing, and that would be transverse velocity. So, starting from this wave function, which would be y equals to 0.12 sine pi over 8x plus 4 pi t. If I take the derivative as a function of t, I would get the transverse speed, the speed of the medium as it's moving up and down. And for all x and t, the derivative of the sine is the cosine. And then by the chain rule, I have to take the derivative of what's inside the parentheses as a function of t. So that will give me another 4 pi out front. So I have 4 pi times 0.12. Simplify this a little bit further. And so I have my velocity, transverse velocity is 1.51 cosine pi over 8x plus 4 pi t. That's my transverse velocity for all x and t. Let's say I go one better. My transverse acceleration will be the derivative of the transverse velocity as a function of time. So if I take that derivative of the cosine is a negative sign, and then again I have to use the chain rule to take the derivative of what's inside the parentheses as a function of time. The x acts like a constant, so I end up with another 4 pi, and that gives me a negative 18.94 sine pi over 8x plus 4 pi t. So this is my acceleration for all x and all time. At the particular point where x is equal to 1.6 and t is equal to 0.2 seconds, my velocity would be 1.51 cosine pi over 8 times 1.6. So the 1.6 divided by 8 will give me a 0.2. So I have a 0.2 pi plus 0.8 pi, which give me pi. inside the parentheses. Cosine of pi is a -1, so this velocity is a -1.51 meters per second. And my acceleration, again, inside the parentheses, I'm going to end up with pi. Sine of pi is 0, so my acceleration is 0. So the string is going up and down. At this point, I'm at maximum velocity and no acceleration as the string is going up and down. So it's looking like simple harmonic motion at any particular point. And if the velocity is negative and maximum, then the string is on its way down at this point, passing through that middle equilibrium point on its way down where it has no acceleration at that point. Here's our wave function again. What's our wavelength, period, and propagation speed? Well, we can look at the wave number and extract the wavelength. We know that the wavelength should be equal to 2 pi over the wave number. So 2 pi divided by pi over 8, which will be the same as 2 pi times 8 over pi. Pi's cancel out, and I have 2 times 8 is 16 meters. So our wavelength for this wave function is 16 meters. I can get the period from the angular frequency. I know by definition the period is 2 pi over the angular frequency. That's going to be 2 pi over 4 pi, or 0.5 seconds. Frequency is 1 over the period, so frequency should be 2 hertz. Our velocity of propagation is the angular frequency over the angular wave number. 4 pi divided by pi over 8. Pi's cancel out. 4 times 8 is 32 meters per second. Now I could have gotten this by wavelength times the frequency as well. Wavelength is 16. The frequency, 1 over the period, is 2. So we have 16 times 2, 32 meters per second. And this wave is traveling to the left. All right, so that's about everything you would ever want to know about a wave function. How we can extract the wavelength, the angular frequency and period and frequency of the wave, its velocity of propagation, and if we start taking derivatives, we can get the transverse velocity and the transverse acceleration. Many times we're speaking of waves on a square root of t over mu. And this is t is different, though, from the t that we've been using earlier in this chapter. We've been using a t that is designated by the period of the motion. This t, though, is the tension in the string. So try to keep those straight. I thought about using the F for force of tension, and I thought that's more confusing. So we just have to keep these straight. In this formula, the velocity of waves on a string is the square root of the tension over the mass per length of the string, which is the intrinsic property of the string itself. By the tension, if you actually put tension in as a force with those units, kilogram meters per second squared, and then you put the mass per length as kilograms per meter, then you would end up with the square root of meter squared over second squared, and you end up with the proper units for velocity, meters per second. So it would work out. So this is a nice little formula. Let's try it out. Transverse waves with a speed of 50 meters per second are to be produced in a taut string. A 5 meter length of string with a total mass of 0.06 kilograms is used. What is the required tension? Well, we're given the length of the string and its mass. We can figure out its mu, its mass per length. That's going to be 0.06 kilograms divided by 5 meters, or 0.012 kilograms per meter. That's our mu. We know that there's a relationship for the velocity of propagation. It's equal to the square root of the tension over the mass per length. If I reverse engineer this equation and solve for the tension, so I'm going to square both sides and then multiply both sides by mu, I would get that the tension is equal to the velocity squared times mu. If I want waves to travel at 50 meters per second, then I would have 50 squared times mu, 0.012 kilograms per meter. I would need a tension of 30 newtons in that taut string. So I'll string it to that tightness, and then I know as waves travel along that string, they are moving at 50 meters per second. Another little formula that we want is the power transmitted through a string. Because we've been talking about waves as being energy transmitted through a medium. So if you were to measure that energy as a function of time, energy per time, you are really talking about power. So we want a formula for the power transmitted through a string. Your book spends a lot of time on this, developing this formula. We're just going to give you the formula and then explain why it makes sense. So here's the power transmitted through a string. It's 1/2 mu times omega squared, the angular frequency squared, times the amplitude squared, times the velocity of propagation. Now we can think of this. Since omega times a is the maximum transverse speed, I mean, if I'm thinking as I'm focusing on the string, as the wave is going by, the string is going up and down like this, like simple harmonic motion, that in this motion, the maximum speed occurs right at the equilibrium, and that speed is the angular frequency times the amplitude. So I can think of this part of this formula as the maximum transverse speed squared. And so now I can write this power formula as 1/2 mu times the maximum transverse speed squared times the velocity of propagation of the wave. Now this first term, 1/2 mu v sub t squared, I can really think of as being the maximum kinetic energy of the string oscillation per length. And if it's maximum kinetic energy, that is the energy per length of the string, times the velocity of propagation, which it would be length per time. So I have energy per length times length per time, and that gives me power. Power is energy per time, or energy per seconds in this case. So I have power. This formula does make sense as in terms of total energy per time being transmitted on this string. Let's try this formula out. Here's a problem. A taut rope has a mass of 0.18 kilograms and a length of 3.6 meters. What power must be supplied to the rope to generate sinusoidal waves having an amplitude of 0.1 meters, a wavelength of 0.5 meters, and traveling with a speed of 30 meters per second? We're given a lot of information here. We got the mass and the length of the string, so we can get our mu, our mass per length. Let's do that. 0.18 kilograms in 3.6 meters. We have a mass per length of 0.05 kilograms per meter. So far, so good. We were also given the wavelength and the speed of propagation, so we can get the frequency from that. So our frequency is the velocity divided by the wavelength. 30 meters per second divided by 0.5 meters is 60 hertz, 60 per second. And from the frequency, I can get the angular frequency. Multiply the frequency by 2 pi, gives me the angular frequency. So my angular frequency is 2 pi times f, or 120 pi radians per second. Great. So I have mu, I have the angular frequency, the amplitude was given, it's 0.1, and the speed of propagation was given as 30. So I have everything I need to put into the power formula. So let's do it. Here's our power formula, 1/2 mu omega squared a squared v, 1/2 mass per length, 0.05 kilograms per meter, angular frequency, 120 pi, square that, amplitude, 0.1 meters, square that, velocity propagation, 30 meters per second. Everything is SI units, so I know that my power is going to come out in SI units, and then come up with 1070 joules per second, which would be 1,070 watts. So these are two little formulas we add to this whole discussion. Formula for waves on a string, which we're going to prove that formula in the next chapter for the velocity waves on a string. And then this little formula for the power transmitted along a string as well. One last idea, superposition of waves on a string. We wish to employ the superposition idea to the concept of waves on a string. Superposition is a concept used often in science, used often in physics, where you look at the individual contributions and you superimpose them together, take them and add them together, and come up with the net result of everything. In this case, if two or more traveling waves are moving through a medium, the resultant wave function is the sum of the individual wave functions added together. So we just look at the individual contributions, add them together, get the net result. Let's see how this might work. Let's say I had one wave traveling along and with its own distinct properties, and I had another wave traveling along as well in the opposite direction. So they both are individual waves with their individual wave functions y1 and y2 respectively, and they're about to meet. Now as they meet, they constructively interfere, and there might be a moment, like under C here, where we have a wave pulse and we took a snapshot at that moment. We would see this pulse, and we would not be able to distinguish at that moment the individual properties of each individual wave. We would just see the superposition of the two together. But a moment later, wave y1 moves along on its merry way to your right, and wave y2 moves along on its merry way to your left, retaining their individual characteristics. So it's only when they interfere that the superposition of their two wave functions add together to give us the net wave function. So they haven't lost their identities, but we can superimpose them together, and we're going to use this principle in the next couple of chapters when we deal with more waves. So that is the end of chapter 16 lecture, and try your hand at some problems, and we will see you again soon.